A shaft of diameter equal to 15 mm and length equal to 100 mm is subjected to the following loading. If SYT is equal to 280 megapascal, you have to find out the factor of safety using a distortion energy theory. This one is slightly typical problem because the loading is complex loading. We have one axial load is acting equal to P, which is 4 kilonewton. One transverse loading is acting is equal to F, which is 0.55 kilonewton, and we have torque twisting moment equal to 25 newton meter. To apply the distortion energy theory, first you have to identify where we have a critical element. Either we have a critical element on the top or on edge, that is either at A or either at B. Or same is true for bottom and on the other side. So all these elements we are taking on the outer fiber. Because for outer fiber, the bending stress will be maximum as well as shear stress will be maximum. So you have to consider the critical element at outer fiber only. We'll fix up our system first here. This one is our x-axis. This one is our y-axis. And along the length, we'll take our z-axis. So this force P will develop here the normal stress. This force F on the area A will develop the shear stress. That is the normal shear stress. And the torque will develop the pure shear stress. To find the stresses here, we'll develop the BD. For this one, we'll cut the shaft at the end. So this one is our fixed wall. On this one, we'll show our circular element. And to this circular element, we'll slightly show the thickness so that I can draw here three-dimensional stress element. So this one is our thickness shown. This one is the top point A and it's a three-dimensional. So we'll show the three-dimensional. This one is point A and one point you have to show as a B. So this one is our face here and this one is perpendicular. So we have drawn here one cube. This one is element B. This axis is same as our x-axis. This axis is same as our y-axis. And this one is a shaft of length equal to L. And through the center, we'll join this center, that is our central axis. So this point is same as the center. So you have to show the action and reaction forces. P force is directed towards the z-axis. So this center will draw here one line parallel to z-axis. This one is representing the force P. This one is action. So this one is reaction. So through the center, we have to show the force equal to P. This force P will produce the normal stress on the entire area, and the distribution of a normal stress is uniform and it will act on this face which is perpendicular to direction of P. And this normal stress is same as equal to P divided by pi by 4 d square. So this force P produces the normal stress on both A and B, and that will be uniform because the normal stress distribution is uniform over the entire cross section. So both element A will experience this stress which is equal to sigma x1. I will say x1 will be equal to P divided by A. And same is true in the case of B also. So the fiber, whether it is at center or at periphery, doesn't matter in case of normal stress, and this value is also equal to sigma x2 is equal to P by A. So we have sigma x1 is same as equal to sigma x2 is equal to P divided by area, which is 4 times P divided by pi d square. This time we have given the value of force P, which is equal to 4 kilonewton, is 4000 divided by pi, and we have diameter is given as 15 mm. So multiplied by 15 square. This answer will be Newton per mm square. That will be megapascal. Is 22.63. So one by one force you have to shift and then you have to find out the stress. Now this force F here will be shown in this way. That is along the negative of x-axis. So here also you have to show the reaction. Reaction will be like this. That will be equal to F is on the positive x-axis. Because of this, we have again you have to show the reaction on the cross-section area. This force is equal to F. This force F will produce the shear, but the magnitude of the shear force is very small. So we will neglect the amount of the stress produced due to shear. So this force F will produce the shear, but the contribution of this force is very small because the value is only 550 Newton. Hence we will neglect the shear due to F. This force F above the y-axis will produce the bending moment in this direction. That is, this force will produce the bending moment in this plane. This plane is same as XZ plane. That is, the bending moment is produced above the axis Y, and this bending moment is this direction. That is, according to the y-axis, this will be anti-clockwise. So the reaction will produce here will be in an opposite sense. So this one is action. Action is this direction. So we have reaction is this direction. So this one is reaction moment. And this value of moment is same as F into L. So this reaction, again you have to show the reaction here. And that reaction will be opposite of this. Now this time it's a clockwise, so you have to show it anti-clockwise. Now the arrow is pointing in this direction. It means that it will going to bend above the y-axis. So we have a distribution of the bending stress. So in this case, this AC will be the neutral axis, and we have maximum stress is produced at B or at point D. And at point D, we have compressive stress, and at point B, we have tensile stress. Now check in this figure. This one is A. This point is same as C. This point is same as equal to B. And this point equal to D. So this axis is a neutral axis. And the bending stress is produced at point B will be tension. And at point D, it will be compression. So tension I will show like this. So this is a slightly complicated idea, and in this case we have a compressive stress is produced. So this one is perpendicular to this plane, which plane is XY plane. That is, on this face again we have a bending stress produced. This one is tension, and at point D it will be compression. At point B it will be tension. Whereas at point A it is on the neutral axis, so bending stress will be equal to 0. So at A and C, bending stress will be equal to 0 because both point lies on neutral axis. Bending stress at point B is positive and is the maximum value, that is tensile. And the bending stress at point D will be negative value, and it's a compressive. So either we can go for B, because already we have the tensile in nature. So we'll select B. Positive will be more value. So we'll select here B point. So at B already we have the sigma x2 is produced, which is 22.63 and is a positive value. And bending stress at point B due to bending will be again a positive value. And therefore, if we consider the positive and positive, then the stress at B will be more. No bending stress is acting at point A, so stress at A will be lower value. So critical point here is B point. So at B we have maximum bending stress is given as sigma B maximum, and for circular cross section this value equal to 32 times m divided by pi into d cube. Whereas the bending moment is given as product of F into L, so we have 32 times F multiplied by L divided by pi into d cube. That is, we have 32. We have force F is equal to 550. So we have 550 multiplied by length. Length is equal to 100 divided by pi, and we have diameter equal to 15 cube of it. So this will give you bending stress. This value is equal to 166 megapascal. So I will show here the bending stress plus the normal stress. So we have this value is same as equal to the bending stress. This value is equal to sigma x2. So total stress acting on phase B will be equal to 166 plus sigma x2 is 22.63. That equal to 188.63 megapascal. And the same stress will act on other side also. And one last effect you have to show is a torsion. So torsion is shown is acting on the free end in this direction. That equal to torque T. So if you look from the Z axis, it will be anti-clockwise. So on this end, it will be clockwise. It will be like this. If it is a clockwise, then on this phase, it will be anti-clockwise. So I will show the anti-clockwise phase of the torque. Now we are interested in the member B only, so the shear stress will act in a vertically downward direction on this phase, that is it will act in a downward direction. So this one is a shear stress. If it will act downward, then it will act upward and the shear stress will get cancelled. In this fashion we can develop our state of stress. We have to calculate here the shear stress is equal to tau xy. The diameter of the shaft is 15 mm and the applied torque is 25 Newton meter. This value of tau xy will be same as 16 times T divided by pi into dq. That is we have 16. Torque you have to take in Newton mm is 25 into 10 to the power 3 divided by pi into d cube is 15 cube. Solve this, you will get the shear stress is 37.7 megapascal. Now you have to calculate here the factor of safety using the distortion energy, and we have given the value of SYT is equal to 280 megapascal. So we want to calculate here the three principal stresses. So here we'll calculate first the two principal stresses. For this one we have sigma average will be equal to sigma x plus sigma y divided by 2. As such, there is no stress acting along the y direction, sigma y will be 0. So we have sigma x equal to 188.63 plus 0 divided by 2. That is equal to approximately this value is 94.3 megapascal. And then we can calculate tau max for the given plane of stress, which is given as under root of sigma x minus sigma y divided by 2 whole square plus we have tau xy square, everything in the under root sign. That is we have under root of, so we have sigma x is 188.63 divided by 2 whole square, sigma y is 0, plus we have tau xy is 37.7 megapascal square. So we will get the value of tau max equal to 101.7. This one is plus minus value. So 94.3 megapascal plus 101 will be positive value. It's 94.3 megapascal plus 101 will be negative value. So that value will treat as a sigma 3 value. So here you have to find out the three principal stresses: sigma 1 greater than equal to sigma 2 greater than equal to sigma 3. Out of that, sigma 1 will be equal to sigma average plus tau max. Then sigma 2 will be equal to 0 because sigma 3 is come out to be negative value, and we have sigma 3 equal to sigma average, which one is a positive value but a lower value as come minus of tau max. We have sigma average equal to 94.3 and we have tau max equal to 101.7. In this case we have sigma 1 is very close to 196 megapascal. The second value will be sigma average will be 94.3 minus tau max is 101.7, that is approximately equal to minus 7.4 megapascal. Using sigma 1, sigma 2, sigma 3, we can calculate the von Mises stress, which is given as sigma prime equal to under root of sigma 1 minus sigma 2 whole square plus V of sigma 2 minus sigma 3 whole square plus V of sigma 3 minus sigma 1 whole square. Everything is divided by 2. Take the under root sign. So V of sigma prime will be equal to under root of sigma 1 minus sigma 2 is same as 196 square plus sigma 2 is 0, sigma 3 is negative, negative become positive is 7.4 square plus sigma 3 is minus 7.4 minus sigma 1 is 196 and we have to make a square and is further divided by 2. So this answer is very close to 200 megapascal, approximately is 199.9, and therefore we have factor of safety by distortion energy theory will be same as equal to SYT divided by von Mises stress. In this case we have SYT is equal to 280 divided by 200. So we have factor of safety will be equal to 1.4. So in this fashion the complex loading will be handled step by step. Your whole idea is to identify whether the A is a critical or B is a critical. Where the normal stress and the shear stress will act, that point will be more critical point. So you have to always take here more critical. That is the highest stress element. That is in this case will be B. There is no normal stress is acting at point A because A is lying on the neutral axis and the video you are watching is from the app, which is the Mohod class app available on Google Store. And in this app, we'll cover all subjects involved in mechanical engineering for GATE. Join the course directly from your mobile. The link is given here.